the last lecture in our semester. And yeah, so today I would like to finalize what we started last week with an example how to synthesize phenylbutadiene. I will shortly repeat what we've done there and then do some other topics in repetition quickly. However, there should also be the chance, if you have any questions, don't hesitate to ask them. And you might not be the only one who haven't understood it, so that there might be also others who might be interested to learn about the answer. For the examination, once again, examination will take place next week on Thursday. Yeah, on Thursday. And it will be at 10 o'clock, and the Audi Marks 2. Fernando and a second PhD student from our institute will be your supervisors, and you can ask them questions. Oh, well, they won't give you the answer, but if you don't understand anything, there might be the chance that they explain a bit more. And yeah, so as already pointed out last week, the type of questions you get, the type of task will be identical to what we're doing here on the whiteboard, on the blackboard, in the lecture hall when it was present, and the things that we discussed. And you may need to make use of your knowledge on the overall topic. Yeah, and so that's the point where I would connect to last time in a moment. But first of all, is there any open question from your side that I can answer?
I have a question.
Yeah.
So are we expected to
know about the basically like drawing the structure of the compound, just if you just give the name of the compound. So like if you give like some, you know, methanoic acid, and we're supposed to know how to draw the structure by ourselves, or do you give the actual structure of the compound?
Well, normally, if you need the knowledge about a compound to answer the question, the compound will be drawn in a structure drawing, like what we've done it all over here in the classroom or digitally. And there might be a number to it, and maybe the text has the name of the structure of the compound, but you don't need to translate a compound to structure or structure to name.
Okay, thank you.
So it will be, yeah, we finalized the exam, the written exam already, and I think, Fernando, but maybe you can check back. I think we don't have any scenario where you need to translate it backward or forward. So normally you get the structures. Any further questions?
I have one question. Is it some of the chemical reactions that we have done that we have studied, they are the equilibrium, like the forward arrow and the backward arrow, and some are like only in one direction. So if do we have to remember all of these, or it's all right if we make one or two mistakes?
Well, mistake, as you say, a mistake is a mistake. But yeah, so in principle, every reaction is a reversible reaction backward and forward. The question is where the equilibrium is lying, on what side, starting material or rather on the product side. And in this respect, so if you remember cofactor regeneration, there are two different types of cofactor regeneration. There was a difference where the equilibrium position is, and this had some reaction engineering implications. So this could be points that you might need to address. But yeah, does this answer your question?
Yeah, I think so. Yeah, thank you.
Okay. Further questions? Okay, I don't see any further questions. Then I would go to share my whiteboard. Up. Go. Yeah. So this was the example we were discussing last week. So the idea was that we have this phenylbutadiene compound up here, and the question is, how can we synthesize this? And this will be one, for sure, I can guarantee you, one question in the examination, but with different structures, different reactions. You need to give substrates, products, and the enzyme class always. And there we started out last week with the transferase versus enzyme class 2. And we found out, okay, there are two possible reactions. So we can either run asymmetric synthesis. There we are starting up from the ketone, and to the ketone amino function is transported and complement the outer product, which is phenolphthaleamine. That's our target product up here. And we have a side product, what is coming out of the alanine, the amine donor. And so the point is that we have in principle theoretically 100% yield. We assign it as a name asymmetric synthesis. We discussed alternatively to alanine, we could also use, for example, isopropanol. And this we could, for example, separate via in vitro product removal with stripping. What would be an easy process layout to do so. Then the alternative second reaction called catalyzed transferase is that we would not start up from a ketone, but we would start up from a racemic phenolphthaleamine with an enzyme, the transaminase, which is just reacting with one of the two enantiomers, which are one-to-one in the kinetic resolution in the racemate, and this would then be a kinetic resolution in contrast to asymmetric synthesis. And here we get at the end three compounds, namely the unreacted enantiomer out of the racemate. We get the new reaction product, which has reacted with the wrong enantiomer, what is the acetophenone, and we get in this case alanine as a side product. And the big difference between those two pathways is that we need enantiocomplementary transaminases, because in the asymmetric synthesis, this is the S product that is asked for. So we need an S transaminase generating the S product. In the kinetic resolution, the S compound is the unreacted leftover. Therefore, we need an R-specific transaminase to transfer away the amine from the unwanted enantiomer. Yeah, this is where we ended last week. Now, before we continue, maybe on this example, namely the second point, the kinetic resolution. There we can once again think about kinetic resolution asymmetric synthesis. So the topic we're discussing now will be on the example of the transaminase, the difference between kinetic resolution and asymmetric synthesis. And if we do so for the analysis, if you remember, we always generate a plot where we plot in the end the EE, enantiomeric excess, as function of the conversion. And these we're normally plotting from 0 to 1, or 0 to 100% if it's 100%. So that here we have 0.5. And in a kinetic resolution, we said we will see under ideal conditions such a course for the residual enantiomer. Residual enantiomer that is not transformed, not converted. If we have more ideal conditions, so let's assume we have an E of 35. Remember how net activity was defined, what is the ratio of kinetic constants reacting the S and R enantiomer, so we are not that selective. Then this course of reaction would need higher conversion to reach 100% DE, because also the wanted leftover enantiomers react in a way because the enzyme is not so selective as we would like to see it. In contrast, if we take a look at the aromatic synthesis, and we assume that the aromatic synthesis is totally enantioselective, there we would just produce the right enantiomerase reactant product. And so we would draw this in here, we would get over the whole range 100% E enantiomeric excess. And as you remember, that you should always be aware of how was the E defined. That was the concentration of the S for dominant enantiomer minus the concentration of the other enantiomer divided by the sum of both enantiomers. Yeah, and this in the end is a plot where we show E as function of conversion. Any questions to this point? And it would be better if you ask questions in contrast to writing the chat, because it's easier for me to recognize that I opened up also the chat window. Okay, perfect, if there are no questions. But there's a second point that we can compare, and that is asymmetric synthesis to kinetic resolution once again. So second point to consider, transaminase. Kinetic resolution to asymmetric synthesis. And here we could generate a second plot. And that is that we're talking about the yield as function of conversion. And let's do this first for the asymmetric synthesis. And for sure, it's once again from 0 to 1 in both cases, so 100%. So in asymmetric synthesis, the conversion, the yield is linear dependent on the conversion. Why is this? Well, in the end, we're assuming ideal conditions. And in doing so, we have no side product being formed. In consequence, because no side product is being formed idly, we have a selectivity of 1. And that is the key point here. Reaction selectivity of 1. Now the question was, why do we have a linear correlation and there you need to remember one of the first lectures, because we said the yield equals conversion times selectivity. So if selectivity is 1, then yield equals conversion, and therefore we have a linear correlation. In kinetic resolution, the situation is different. Kinetic resolution. Here we do have under ideal condition once again. Meaning also ideal condition once again, no side product being formed. But we have a one-to-one mixture of the two enantiomers. And in consequence, only one enantiomer is reacting. So we have max 50% yield. Now, the point is how to assign yields. And so we cannot say if we have a one-to-one mixture of the enantiomers that at time point 0 we have 50% the right enantiomer in there, and in consequence we already have without any reaction 50% yield. So yield always is assigned to what we have at the end of the reaction, isolated or in solution of this fraction. Therefore, we're talking of the residual fraction of a compound, and these we express as C divided by C0, and that is the residual concentration fraction. Now of our enantiomer we're looking at, and so if we just say once again approximately here, that it will cross here in the 50% section, not so nicely drawn, but you know what I mean. Then if we now express the real concentration fraction of the right enantiomer, that would be constant in terms no reaction, because that's not reacting. Then 50% conversion, we have at the end 50% yield, because the other enantiomer is totally reacted. Okay. Any questions to this point? Okay, I don't hear or see any questions, then we will proceed. Now we're back to our story. The story is that we would like to synthesize phenyletilamine. So let me redraw the structure up here we're focusing on. That was a question in the task I gave to you. So now we had transaminase EC2 enzyme. Do you have any idea how you could produce this compound with an oxidotase?
Yes. We will take the ketone, and then
yeah, that's right. So we will start out with the ketone. So I'm just your just right term, what you have to do in the examination by yourself, but you can dictate me. That's a nice thing, huh? So what do we need additionally to do so, and what's the enzyme we're applying? For sure, the product I already know.
ADH.
Yeah. So we need a cofactor to do the job. AH, right? So what other compounds generate or need or whatever?
We will generate the alcohol.
No, we're not generating alcohol, we're generating the amine. So you're right, normally often we do the reduction of the ketone, so often we have the reaction going on that we are running this and producing out of this the corresponding alcohol, yeah? Absolutely right, this would be this alcohol dehydrogenase, but the difference to here is if we add to the system with some specific enzymes ammonia, we do what we named reductive amination. We had this on the example of leucine dehydrogenase, on the example of the Evonik older-fashioned name, the Degussa process. And the enzyme is an EC1 enzyme, so namely an oxidotase by class. It will be respectively specific carbonyl reductase. And the co-product we're getting out of this is NAD+. And then we still need a side product. And now if you're looking at the function that is being predictively aminized, the amino function and the amount of protons you have and the oxygen atom, so the side product here will be water. So we just adding this up here. And so that in the end, the overall yield, it's an asymmetric synthesis. So exactly what we had discussed here. So the yield, possibly under ideal conditions, will be 100%. And so that would be already the right answer to this part. But now the question would be, this one is much too expensive. What can we do to make this more economically attractive?
We will run the racemic mixture.
Yeah, we could use a racemic mixture, but let's say I'm happy to start up with this acetophenone. That's okay. Yeah. But I was wondering, this one is pretty expensive, so we pay about $2 per gram of compound.
Then we will regenerate.
Yeah.
Then we will regenerate.
Yep. Right. So then that would not be part of the task that I've given you here. So here the task was to name substrate products enzyme class. Yeah. But yeah, we need to know the concepts and need to understand what we can do to make it more economically attractive. And right, you said NADH cofactor generation. Therefore, the point to answer to this question would be cofactor regeneration. So what would you do here?
I would go.
Maybe also someone else can answer if someone else likes to. Okay, I don't see any volunteers, so go ahead.
Maybe I would go with the, like in the oxidoreductase we went for the isopropanol, but here we will go with with the isopropanol and then.
Okay. So what's the name? What's the name of the cofactor regeneration where you use isopropanol?
Substrate coupled regeneration.
Perfect. Substrate coupled. And you might use the same ADH or carbon reductase, yeah. And so the bottom part, there would be already said isopropanol. We're linking in here. That would be the bottom part going below, and the side product we're generating at the top. Yeah. So this would be the part. Then you just started up, but I stopped you. You also have a second best alternative, right? Or not a best, second best. You have a second alternative. What would that be?
Enzyme coupled regeneration.
Yep, right. And what would you apply here?
Some second enzyme, FDH, GDH, any other enzyme.
Yeah, absolutely right. And in the end, let's say we're just playing now with FDH.
Then always carbon dioxide.
Yeah, perfect. Okay, so in the end, what is the starting material you're using there?
Formic acid.
Yeah. Yeah, that's it. Okay, so we got to know now for this question 2 possible answers. that for one is transaminase enzyme class 2 and oxidase enzyme class 1. Yeah, and we have a question by Emilio.
I was just wondering whether you could explain again why this was kinetic resolution.
This is not kinetic resolution.
That was also what confused me. Well, that was what you said.
No, this is asymmetric synthesis.
Okay, then I got it because I got a little confused.
No, sorry, maybe I mispronounced or used the wrong words. I don't know. I hope not. But this is asymmetric synthesis, and because of this, we have the 100% possible yield. And that was what we're looking at here. So this is the asymmetric synthesis. Yield is function of conversion, and if we're looking at the residual concentration fraction, then we're starting with racemate, and we would be only 50 max under ideal conditions. Okay?
No, could you repeat that last thing you said about with the red line?
Okay. So once again, let's stick to asymmetric synthesis still a moment, because if you need to understand this. So we plot yield as function of conversion. Okay. Now for asymmetric synthesis, meaning with the activity is 1, we have no side product being produced. Meaning starting material is directly only transferred to the product. If this is true, conversion equals yield because the activity equals 1. Okay? Along with this?
Yes.
Okay. In consequence, we have a direct correlation between yield and conversion. Now, kinetic resolution, your question. We're starting up with a 1-to-1 mixture. Yeah. So only 50% can be our target. So this was in the end what we have seen down here. We started up with racemate. The R transaminase just transforms the R starting material in the R enantiomer to the acetophenone, and the S enantiomer is not transformed as at all. It's left over. Okay, just dead, lying around and waiting that the wrong enantiomer has reacted away.
Yes.
Okay. Until that point we are clear. Now, back to the plot. So under ideal conditions, we have no side product. So the one enantiomer reacts over, and now we are in the situation that we have the wanted enantiomer just left over, and in consequence, since the right enantiomer is left over, and this was a 1-to-1 mixture, we can only have 50% maximum yield. Okay, this point?
Yes.
Okay. Now you might be confused about this residual concentration fraction I've drawn here, right?
A little bit.
In contrast to the yield. Now,
I'm also confused by the fact that you're saying that we have a straight line.
Yeah.
Or it's because I'm looking at the wrong reactant, because the no that can rise horizontal.
The reaction, yeah, product is not our target compound in the kinetic solution. Yeah?
Okay, makes sense.
Because
yes.
we're starting up with S and R, so I could also draw it once again down here. Let's say I've got an S plus an R enantiomer, and those have a ratio of 1-to-1. Okay. Now we have 1, which is not reacting. Yeah. So therefore, we have the S left over. But the second one we have reacted to a product. Okay. That's the other enantiomer. Now, this is our target compound. Even this was the reaction product. This is the one we give to the customer. Okay. Therefore, since it's not a product, we can also not talk about the reaction yield, if you pronounce it in a hard manner. It is this one that's left over, and therefore it's a residual concentration fraction. And this residual concentration fraction will be 50% concentration of the right one in relation to the concentration at time point 0. And therefore, it's constant at 50 over the conversion.
Okay, that makes sense. I thought about it as you always look at substrate when you look at that plot. Okay, thank you.
But thank you. It's good to hear that what I say makes sense. Okay. Yeah. So now we have seen two possibilities. For one, we have oxidase, we have transaminase, EC1, EC2, but now we have further possibilities how we could run here. And so number 3. Yeah, what could that be? What enzyme can we also once again apply? What enzyme can we apply that we did not discuss so far to produce our target product? What do you think? No one, any idea? Well, we have, maybe you go through this. We have 7 enzyme classes, and we talked about enzyme class 1 and 2. And now we're looking for any possibilities from 3 to 7, what you could still do to get our customer happy. No one has an idea? Yeah.
Is it possible to use a hydrolase to break a C-N double bond between the carbon and then the NH2 to
we only have So first part is right. So let's take this. We take an EC3 enzyme, a hydrolase, and I would suggest we start up with a lipase, for example. Yeah. So let's say we have 3.1. Yeah. We can now think about different reactions we're running. And the most simple reaction we also talked about was, at the end of the day, hydrolysis. Yeah. So the question is, how could a starting material look like where we apply lipase to generate our target product, which has an S configuration.
Ester, maybe?
Yeah, good. So any kind of ester or so to start up with. And since I said hydrolysis, we want to take hydrolysis. For sure, we already know if we do hydrolysis, we always need water. Yeah. One step forward. So what could be the compound? You said ester. The name in English is a little bit of the chemical is a bit different, but it's the right approach you're picking. So the starting material will be our racemic amine. Therefore, I'm drawing this waved line there once again. And here we have now acetic acid or any kind of acid being attached. Just to remember, in terms of names, ester, that was this compound. And then we have any residues on the left or right side, ester, And if we have the nitrogen involved, then we name the same structure, but with the nitrogen, we name amide. So ester amide, okay? And since the amide was group, the table group number 5, we have here hydrogen. So that would be the standard ester function. So this is exactly this one, what you see here. And both compounds, the ester, this functional group, as well as the amide, you can cleave with water, just split it into parts. And the one way, if we have an ester, we generate out of this the alcohol, and we have an amide, we generate out of this the amine. Okay. And by the way, spelling already, sorry. So the amide in English has an E. So, okay, so this is our starting material, and the starting material is racemic. Therefore, we have this waved line here. It's racemic. Meaning, we only have, it's a one-to-one mixture, as explained beforehand. And now the question is, what would be the reaction products be? So who could describe those?
One of the product you have already write it down, and the other product would be the remaining R of the same reactant we are using.
Right. So this one is really a reaction product, and the one I'm drawing right now is nothing more than the unreacted starting material being left over, what we just discussed with, I think Emily was the name, so it was a lady we just talked about before. So that is the other enantiomer being left over. But we're still missing something, so we still need one reaction product additionally.
The acid, amide acid.
Right, what we have split off of the amide, the acid. Right, and now if we're looking at the structure, and this amino function stays still here, and we add the hydrogen, the water with the oxygen, so it will be the free acid in consequence. So the reaction product will be this product. Yeah, and this is what we name, once again, without repetition, we just had it before, some minutes, kinetic resolution, and then it should trigger off directly EE as function of conversion. So it's once again true what you already have drawn here. Okay. Now the course that we have drawn here for an ideal situation for E35 was that of the product enantiomer or of the unconverted enantiomer. So the course we've just seen is this compound, or is it this compound? Okay, it could be down here. It's easier to discuss. So we just had this course EE 0 to 1, 0 to 1 conversion. We get 50%. So that we said under ideal conditions, this is this course. My question to you: what enantiomer is this? Is this now the reaction product, or is it the leftover unreacted one, the course that we see here?
reaction product?
Yeah, also Chitama is writing the R because it's conversion, right? So, no, sorry. This one is not the reaction product. That one is the leftover, yeah, unreacted. And what is written in the chat by Christoph is right, that the R enantiomer, because so this one has the R specificity, yeah. That is the leftover. So this is leftover. This is the reaction product. And what we see plotted here is the course of the leftover, because we're starting up from the one-to-one. We have the wrong one reacting away, that's namely the S, and we're increasing the atomic excess of the R. So in consequence, what we see here, this compound. This course. Now, last question, what would be the course of the reaction product? How would that look like under ideal conditions? So what would I need to draw in here for the reaction product?
It could be a horizontal straight line.
Straight line?
At enantiomeric excess equals to 1.
Like here, or?
No, on top of the graph.
Why?
Because only the S isomer is produced.
Yeah, right.
So you only have an enantiomeric excess of 1 for the S.
Right.
For the S.
Yeah, absolutely right. So that would be the chords there we're talking about. Perfect. And if you're very unlucky, yeah, well, I don't wish you, but sometimes you are, and you have, for example, E35. So every 35 right enantiomer molecule, the wrong one is reacting, you don't want to run, then you already will start lower here, and it will come down, and for the residual enantiomer, you need higher conversion triggers. Yeah. Okay, I hope you have understood this. Make sure you also understand the difference between the ester and the amide, and then once again, you have more principles understood that you could use. But making use of a lipase, we just have hydrolysis. Would you be able to think about other reactions we can run with the hydrolase to generate this product?
The reverse of the last reaction that we have done.
Maybe someone else, sorry. Anyone? Any idea? Already one thing was already named. So Tayab said, I hope that's right, pronounce your name, said the reverse of this hydrolysis reaction. What would that be? Anyone idea what that's named? If we are
making the esterification again going to the ester. I mean amination.
Right. So if it would be the oxygen, yeah, we name it esterification. And here, if we have the nitrogen, just named amidation. And that is what we have here. Esterification would be if our target product would look like this, an alcohol. Okay, so now if we run the specification, our starting material, or the amidation, sorry, the starting material will be once again our compound here, and we would do it once again in esterification mode. So we would start up with the racemic one. With the racemic one. Would be an amidase, or lipase, whatever. There's some cross activities. Yeah, so what would be the reaction product look like? And what could be the reactant we need?
Because this is the racemic, then one would be the.
Maybe wait a moment and sorry to stop you. Wait a moment and let's see if someone else would like to try. No one?
An alcohol, it'll react with an alcohol.
It reacts with alcohol. So in the end, you just need to go back what we've done here. So here we have this starting material by the help of water. We have split into this product and this side product. And that is an acid, right? And now what we're discussing right now is just the reverse reaction. So in the end, we just would need to have an acid generating our real reaction product, which is the R enantiomer. Plus the unreacted, unwanted left over. Oh, our wanted one, but by the enzyme not wanted one. So that's our target here, the unreacted one. And we generate a side product. Anyone knows what the side product here would be?
Can I answer?
Wait a moment. Give them a little bit more time.
Water.
Yeah, perfect. Excellent. Water. Okay. So, what would be the maximum yield that you would expect in this reaction, the ideal conditions?
That also be 50%?
50%.
Yeah, sure. Because we're starting up with a 1-to-1, and if we react 50%, we have 50% the other one. Absolutely right. Now let's get to
enzyme class would be. The enzyme class.
So
because this is not the cleavage. This is not a hydrolysis.
It's a hydrolase, EC3.
But it's not happening under the consumption of water.
Right. Good point. But wait a moment. Let me get you. I just want to open one old presentation. Just give me a sec. Wrong one. One sec, sorry. I will just skip back to the lecture sometimes before Christmas. this was where we introduced the hydrolases. And we introduced the hydrolases with a hydrolysis reaction catalyzed by lipase with water, where we split an ester, and you see it's an ester, not an amide, because we do have here the oxygen couple, and we produce the free alcohol and the free acids. And now, in that lecture, we said there's this catalytic mechanism. Oh, you don't see much transparency, right?
No.
Yeah, so we have this catalytic mechanism, the acyl enzyme intermediate, and we said, so one rest of this ester is bound to the enzyme. And the enzyme is now cleaved. And this here on the laser pointer, this here on the left side, that's what is clearly named the hydrolysis. So where we have water, yeah, leading up to the free acid. But alternatively, we could also use an amine. And then we end up with an amide, yeah, with an aminolysis, for example. Or if we adding hydrogen peroxide, we form the acid formation. Or if you have another alcohol, we do a transesterification and ending up with a different R on here. So you see, we just need a nucleophile, but historically, this enzyme class 3 is catalyzed, is named hydrolases because it was historically just found out that this reaction was water running. Okay?
Okay.
With you in a sec. So now switch back to my whiteboard. Okay, now we're here with this game, and just fighting with my tools. I just want to insert. Okay, this was the transparency you just have seen. We just grabbed out of the old presentation, right? And now we're in the situation that we do have an acid that is being coupled to the enzyme. So this is the intermediate of this compound bound to the enzyme. And the amine that leads to this pathway is this compound. So we're talking here about this reaction with this amine. What is this amine? Okay. Okay, so that's esterification. Now we have two reactions select this hydrolysis, esterification. So what would be the reaction medium you're scaling your process in for this amidation?
Organic.
Right? And Christoph is writing because water is side product, right? We want to operate it under organic conditions, so we will run it in an organic solvent. Because side product is water. If we would run it in water, we would initiate directly this backward reaction that this will be cleaved again, and in consequence, our enantiomeric excess will get worse during the reaction. And there was from Tobias, there was a question: have we same structure of the S enantiomer on the left side? I do not totally understand what you want to know. Sorry, can you rephrase it, or just open up your microphone and ask directly? Okay, I don't see or hear anything, but maybe to make it clear once again. So this means this racemic drawing, and racemic drawing means that we have this wave line here. It's always a sign of the racemate, in contrast to the dashed line here, or the arrow, or the other enantiomer. So this means that our starting material will be this enantiomer. What is our target? Plus this enantiomer. What is it reacting in our example? And they are named racemic. What we have here. This means we have them in a 1-to-1 ratio. Okay? I hope that makes this clear. So that in the end, this is the S enantiomer, this is the R enantiomer. And this for sure, you should also know how to assign the nomenclature to determine the two enantiomers. Yeah, and the last possibility that we would have here in this game is a further reaction I could think about. That's also once again with a EC3 enzyme, so a hydrolase, formerly by name of the enzyme class. That would be transesterification. Or since we are dealing here with an M-mine, this target would be transamidation. Meaning that in contrast to what we've seen just before, we can now act with the second amine where we're exchanging something. So let's give it a try. So let's say we have a starting material, any kind of an ester. And there we add our racemic waved line, amine, racemic fashion. We have our EC3 enzyme, the hydrolase. And now what's going to be happening in the trans, while it has the trans, that we have here an ester, a starting material. We have here an amine, or a different alcohol, if the alcohol would be the product. And we are replacing this residue here. So we're generating out of this the reaction product itself, which is the amide. Now I should have drawn it the other way around. Now I have to think. Sorry, one moment. So we want to have which one? So we want to have the S. Yeah. So this must be the R enantiomer that has reacted away. And since it's the R enantiomer, this must be drawn here like this. And then we do have left over the unwanted the unreacted enantiomer, plus we have left over the lid of compound, because that's a translocation. This and these residues will be exchanged. Yeah? Therefore, trans. So the further residue will be this alcohol residue, which is the lid of here. Okay. Now you might wonder, why don't we have the dashed line here? But if we go through these two structures once again with nomenclature, just the way how I have drawn it. If we take the lower one, the nitrogen highest priority, if we compare those two carbons, then this one will be the second one, and this one will be the third one. Lowest priority, not drawn, going to the back with the hydrogen bottom. So we do have a left turn. Therefore, this is the S structure. If you're looking to the upper drawing, this is one. The not drawn, chemist lazy, proton to the back, so that is okay. Same argument, this is a higher rated carbon than this one, because the aromatic ring is more carbon-carbon bondages. So if we're looking at this structure, we do have a right turn. Therefore, this is the R drawing. Depends how you draw it on the paper, if you see the dashed line or the big arrow, depending what pointing direction, but it's always depending on the correlation of the individual compounds to each other. Any questions on this? Okay. Yeah, so this was one of the examples, and so this is a little bit like chess playing. So you need to know what we got in the lecture, the fundamental principles, not a very specific enzyme name from a specific strain. So you should need to know, or you need to know the principal reactions, like what we talked, limitations thereof. Maybe one last question to this. First, so the hydrolysis that will be carried out in aqueous solution. Yeah, because we need high amount of water as reaction starting material. What would be the solvent for this translocation if you run this thing? Any idea? Would you use an aqueous-based phase? Would you use preferably an organic solvent? So what would you like to use?
Is it organic because there is a chance for cleaving, like the product can cleave back in presence of water?
Right, so we do not have any water here as reaction product, yeah? But we do have an ester, we do have an amide being formed, and if you would have water present, we could split those here, and this we don't want, we want to prevent. Therefore, we run it in organic solvent to just circumvent reactant, so starting material and product, hydrolysis, lowering overall yield. And the reactant hydrolysis would apply to this one and to this one. Okay? Yeah, then maybe one last thing from my side. And then you would once again have the chance to ask questions. Just a point If to calculate, we have a total turnover number I just want to repeat with you. And let's say we have one specific starting material, which is a hydroxy acid we want to produce. And would like to do this with an enzyme class 1, naming an alcohol dehydrogenase. So in the end, the starting material would be the corresponding ketone. We already had one example of alcohol dehydrogenase before. And remember, we said, okay, we need cofactor regeneration. We require NADH. I just repeated because we discussed it before today, antibus side product. And now we do have 200 millimolar of the starting material that we run in there. We have 0.5 millimolar of the NADH, and we have a conversion in this reaction in our batch of 90%. The question is, what's the value of the total turnover number? What do you think? Maybe first, how is the total turnover number defined? Anyone, any idea?
So I think it would be 200 times 0.9 divided by 0.5, because the total turnover number would be the mole of the product that is produced divided by the mole of cofactor consumed.
Yeah, that's absolutely right. Let me just write it down for everyone to follow. Thank you. So TTN is the mole of the product produced for the cofactor regeneration in relation to the mole of the cofactor consumed. Yeah. And now, assuming we have cofactor regeneration, but that here is our initial investment. Yeah. This we can then relate to. Concentration of product divided by concentration of the NADH constant system, and that would be then as answer exactly like you said, calculating it 360. Yeah. Because it would be 200 millimolar divided by 0.5 would be 400. So this value would be 400, but we only have 90% conversion. Yeah, so 90% of 400 is 360. By heart.
Yeah, maybe write up the equation. You know.
Sorry, once again.
Can you maybe write up the math?
This is what I just said. Okay.
Yeah.
So it would be just here equals. We said we have 200 millimolar of starting material, but only 90% conversion, right? And so that would be then, if you put it in here, 200 millimolar, that's CS0, starting material, time point 0, yeah, times 0.9, what would be the conversion, yeah, because we said it's 90% conversion. That would be 180, yeah, if you calculate this just in your brain, 200 times 0.9 would be 180. and then we just divide, and we just divide it by the mole of the cofactor. That's our investment plus utilization. So it would be divided by 0.5 millimole. 0.5 millimolar. That delivers us 360. And this was always industrially assumed with the cofactor regeneration somehow. Okay. Donald is asking, is 360 a great turnover number value in industry setting? No. So normally industrially you should yield ideally 1,000 or even higher. So even higher is wished for, but 1,000 is something you start up to think about applying it. However, it's a question of the price of the product. So this for sure is what we have here is rather dirt cheap, but if you have very expensive compounds, sometimes also 360 is reasonable, but it's a rather rare case. Yeah, I will load up these transparencies still to the Studio IP. Tomorrow we will finalize the immobilization, the membrane filtration, and then also there we do some practice on some case studies where we make use of our knowledge that we have gained. But are there any questions from you today still? Okay, don't see any in chat, I think, and also not, no one raised his hand. Yeah, so I don't see any questions. So last chance to open up your microphone, otherwise, or write something in the chat. Otherwise, we would close this repetition today, and we will see back again tomorrow morning at 8. Okay, I don't see any further. Then I say thank you very much for every one of you, and see you tomorrow. If you any further questions also to this lecture would come up, I would happily answer them tomorrow morning. Just let me know. Okay, yeah. Then stay healthy. See you tomorrow morning again. Bye bye.
Recording
stopped.
Thank you.
Bye bye. Thank you.
Thank you, Prof.